Hey everyone, welcome back, and in this video we're going to be starting a new topic, which is exponents or exponentiation. Basically what we're going to talk about in this unit is what exponents are, how they work, why they're useful, and of course we'll do some examples with them. Later on in the unit we'll be talking about square roots, cube roots, things like that. Those all fall into the category of exponents, and if I can remember how to do it with confidence, then I will also show you guys how you can calculate square roots by hand. So basically doing it with a pen and paper, the same way that we can divide numbers by hand without needing a calculator for it. I'll show you the same thing for square roots. But basically we'll start with what exponents are. So basically exponents are useful when you are doing repeated multiplication. So exponents, so this is something you can write down just so that you're aware of why we're using these. So exponents are useful in problems involving repeated multiplication. So that's sort of where they come into play. So if you take that a step back, multiplication itself is useful in problems that require repeated addition, right? If I was giving you a problem where you end up having to add the number 2 to itself 5 times, you go 2 plus 2 plus 2 plus 2 plus 2. When you're first introduced to multiplication, you learn that 2 times 5 is the shortcut for 2 plus 2 plus 2 plus 2 plus 2, right? So if you're adding the same number over and over again, we can replace addition in that situation with multiplication. Now it's important that you're adding the same thing over and over again, right? If I'm doing 2 plus 3 plus 2 plus 5 plus 7, I can't use very much multiplication in there at all. So it's important that you're adding the same thing over and over again in order to be able to use multiplication effectively there. Now for exponents, it's a similar idea, but instead of adding numbers, we're multiplying them. So sort of the next step in the chain, you could say that if you're repeatedly multiplying numbers by themselves, so 2 times 2 times 2 times 2 and so on, then you could use an exponent to represent that in a different way. So basically we're going to focus on that idea of exponents representing repeated multiplication, and we'll just do a few examples, nothing overly complicated in this video, just so that you can sort of get a feel for how this notation works, and then we'll talk about a few rules that you have to follow with exponents after that. So we'll start with a couple of simple examples. So here's a simple example for you to see. You might have seen something like this before. So we've got a 2 here and a 2 up there, a little 2 up there like that. So what we have here is this number here is called the base, and some people use different terms, but one of the more common ones is that this big number down here is the base, the little one up there itself is the exponent, and the answer to this, the overall meaning of this, is called a power. So you might have heard things like powers of 2 or powers of 3, things like that. So the same way that with multiplication you can have multiples and powers, or sorry, multiplication or multiples and factors, things like that. In exponentiation we deal with powers, exponents, and bases instead of things like products or multiples or factors or things like that. So a little bit different. It's obviously going to have some differences from things that you've seen before, and you guys have seen a little bit of this in the past with, when we worked with quadratics and stuff. Then you would have seen some squared numbers, and you've interacted with squares and cubes and stuff in your daily life. I mean squares and cubes in the mathematical sense, not like the shapes, even though you interact with those two. But yeah, so in this video we'll just sort of go through some examples of, you know, how to write these different exponents, what they mean, what does it mean to have an exponent of 2, an exponent of 3, an exponent of 5, and how does it change your answer if you change the base or if you change the exponent, what happens. So we'll explore some of that we'll start off with a few simple examples, and then we'll work our way towards some more complicated examples. So if we start with this 2 squared, now what this means is you're going to take the base, so this number 2 down here, you're going to take the base and you're going to multiply it by itself as many times as the exponent tells you to. So the exponent up here, this little 2 up here, is telling us that we have to multiply this guy by itself twice. So that means we're going to have 2 2's written down here. So only one product, but we're writing down the base twice. Now this is a little bit confusing because both of those numbers are the same, but you'll see what I mean in a moment when we do a slightly different example. So 2 squared, that's the way that we would read off this one, which I'm sure you guys are familiar with, but 2 squared is how we would read off this one, and that means we're doing 2 times 2, where this 2 and this 2 both come from the base, this big 2 over here, and the reason that it's written twice is because there's a little 2 up there. That 2 is telling us to write down the base twice, and then we're going to multiply it together. So if we go ahead and do that multiplication, we get that 2 squared, which is 2 times 2, is going to equal 4. Now this isn't necessarily the best approach for a topic like this, because a lot of people tend to think it means you're multiplying the big number here by the little guy up there. And that's not what it means. That's what it means in this particular case. It happens to give you the same answer. If you did this 2 times that 2, it would still give you 4. So it's a logical conclusion if this is the first and only example that you've seen of this kind of stuff. But you should note that it's definitely not that. It is related to multiplication, but not in that way. So let's do a similar example. Instead of having 2 as our base, we'll have 3 as our base, and we'll make our exponent 2 again. So remember, the base is the big number, so we've got our base is this 3 now, and our exponent is 2. So because the base is 3, that tells us that we're going to be multiplying a whole bunch of 3's together. Now, how many 3's? Well, that's where the exponent comes into play. How many 3's we're multiplying together is what the little guy up here tells us. So because we've got a 2 up there, that means we have to multiply 2 of the base together. So 3 times 3. So basically you're writing down the base twice because of this 2 up here, and you are going to multiply those together. So for an example like this one, so we've got 3 squared, or 3 to the exponent 2, is going to translate to 3 times 3. So I've taken this base and I've written it down twice, and I've written it down twice because of that exponent that we have up there. So that's where that comes from. So if we go and do that multiplication, we get 3 times 3 equals 9. And so you can say that 3 squared equals 9. Alright, so that's how this sort of works. We'll do one more example that has an exponent of 2 again, and then we'll move on to using a different exponent. So here our base is 4 instead of 3 or 2 like we had before. Our base is 4 and our exponent is still 2. So hopefully you're catching on now. We're going to write down the base a couple times. So we've got 2 4's down here. We've only got 2 of them because of the 2 up here in our exponent, and we're going to multiply those together. 4 times 4 is equal to 16. And so that's what gives you your answer, is that this 4 squared means 4 times itself. 4 times 4, and we have the base written down twice. So you're not multiplying it 2 times, because that would be 4 times 4 times 4, right? If you're doing the actual multiplication twice, that would mean you have to write down the base more times. So the number of multiplication signs is not necessarily is not going to be the same number as your exponent. It'll be one less than your exponent. The number of times that you write down that base, the number of times that you write down that actual number, is however many times the exponent tells you to. So let's see that with a slightly different example. Right now we've done 2 squared, 3 squared, 4 squared. So we've changed the base, but we've left the exponent the same. So you can see that when your exponent is the number 2, you're writing down the base 2 times, right? And that happens for, it doesn't matter what the base is. Anything squared is going to be that base multiplied by itself, and that's it. That's where you stop, because you only need to write down the base 2 times. So now, let's change it up. Instead of having 3 squared and 4 squared, let's change it up, and we'll keep the base the same, so we'll keep the big number the same, and we'll change the exponent. So now we've got 2 squared, we know, we'll leave that up there for reference. Now we'll change the exponent to a 3. So, if we change the exponent to a 3, what happens? So let me move that equal sign over. So now, what this is telling us is our base is 2, so we're going to be multiplying a whole bunch of 2's together. How many are we multiplying together? That's what the exponent tells us. So because we have a 3 in the exponent, that's going to tell us that we have to multiply 3 of the base together. So the base is 2, and I need to write down the base 3 times, because that's what the exponent up here is telling me. I have to write down this base, this 2 over here, I have to write that as many times as the exponent tells me to. So the exponent has told me to write it down 3 times, because we've got a 3 up there. And the base is 2, so that's the number that I'm actually writing, and then I just multiply those together. 2 times 2 times 2 is going to give me 2 cubed. That's how we read off a number where the exponent is 3. So 2 times 2 times 2, well, 2 times 2 is 4, times another 2 is 8. So that's going to give us 2 cubed is equal to 8. Alright, hopefully that pattern is making sense, that if you increase the exponent, you don't change the number that you're multiplying, but you change the number of times that you do that multiplication. So if we change this one more time, we'll keep the 2 the same again, and we'll make the exponent a 4 this time. So before we were working with 2 squared and then 2 cubed. So here, because we had an exponent of 2, we had 1, 2. We wrote down the base twice. Here we had a cube, we had an exponent of 3, so we wrote down the base 1, 2, 3 times, because that's what the exponent told us to do. So now the base is still 2, so the number that we're going to actually be writing down is the number 2. That part hasn't changed, but the number of times we write it down is what's changing now. Instead of writing it down just twice or 3 times, we have to write it down 4 times, because that's what the exponent is telling us. That's what that exponent of a 4 means. So we're going to write down this base 4 times, so 1, 2, 3, 4, and we're going to multiply all of those together, and then we'll get our answer. So 2 times 2 is 4, times 2 is 8, times 2 is 16. So you can see that these values are doubling. Every time that we go up a power of 2, these are all powers of 2, so every time you increase the exponent by 1, as long as your base is 2, those values are going to double. If your base was something different, if your base was 3 or 4 or 5 or something like that, then your base would triple or quadruple or something like that, right? So the amount that it changes is based on, well, the base, but the specific value is sort of dictated by that exponent, because you could have a huge base but a tiny exponent and get a really small number, or you could have a small base and a huge exponent and you get a really large number. So let's do another couple of reasonably simple examples, but just so you can see this stuff in action. We'll change the base and the exponent. Right now we've been sort of relying kind of heavily on using the number 2. So let's not do that. So now let's change our base. We'll make our base the number 4, and we'll make our exponent the number 3. So to represent 4 cubed, that's how we would read this. So if you've got, some number, I'll just put a box, you put a number in there. Some number with a 2 up there is squared. You're squaring that number. And if you've got some number with a 3, with a little 3 beside it, then we say cubed. And the reason for that is that if you had, well, we can sort of talk about this more later on, but if you had a square, if you had like just a shape, I mean, it is going to be a square, but if you had a shape with, some side length, let's say 6 centimeters, let's say each side of the square is 6 centimeters, that means all of these are 6 centimeters all the way around, then the area of the square is going to be 6 times 6, or 6 squared units. So that's sort of where the squared thing kind of relates to things with shapes, things with geometry, is that if you had a square, the side length squared, the side length times itself, will give you the area of that square. And the thing with the cube thing here is it's a similar idea, but instead of dealing with a square, you add a dimension to it. You're going to make it a 3-dimensional object, which, if every face is a square, then you have a cube. And so that means that you've got a length, width, and height all of 6 units, let's say. So then the area of each face would be 6 squared, but the volume of the total cube would be 6 cubed units. 6 times 6 times 6, length times width times height. You don't have to write that down or remember that. That's just sort of maybe a way that could help you remember what squared and cubed mean as terms, but you don't really have to worry about that too much. Anyway, getting back to this problem, so we're dealing with the number 4 cubed over here. So we've got our base is 4, and so that's the number that we're going to actually be writing down. Now, the number of times that we write it down is dictated by the exponent. The exponent here is 3, so that means I have to write it down 3 times. But remember, you're not writing down any 3s. You're not doing 4 times 3 or anything like that. It's still 4 times 4 times 4, but you only write down the number 4 3 times because of that exponent up there telling you to. So we've got 4 times 4 times 4, we'll put those multiplication signs in there, and then we can get our answer. 4 times 4 is 16, and then 16 times 4 is going to give us 64. So that would be your answer for 4 cubed. Alright, hopefully that's making sense. Now the next one is slightly harder. We'll make our base 3 this time, and we'll make our exponent 5. Alright, so a lot of people, they'll look at this kind of thing and they'll initially make the mistake of, oh, 3 times 5, that's 15, easy, I'm done. It's not that simple. So our base is 3, so that's what we're going to be writing down. And we have to write it down as many times as the exponent tells us to. Now our exponent here is 5, so we're going to be writing down the number 3 5 times. There we go. And we're going to be multiplying all of those together. Note, you can see that it's repeated multiplication, right? It's the same number times itself a whole bunch of times. Writing it with an exponent is sort of a shorthand of writing all of that. So it's 3, I've written the number 3 a whole bunch of times. This 5 up here translates to the 5 times that we've written down the base over there. And we can go ahead and do that calculation to get our answer. So 3 times 3, that's 9. Times 3 is 27. Times 3 is 81. Times 3 is 243. Huh. So you might be noticing now that even though the numbers that we started off with are quite small, our answer is reasonably large, right? So what we've done here, we started with 3 times 3, that's this first one, and this second one is equal to 9. But then we're gonna multiply in this third one. 9 times 3 is 27, and then we multiply in this fourth one. 27 times 3 is 81, and then we multiply in that fifth one, and 81 times 3 is 243. So these numbers start to get pretty big pretty fast. And you might notice that if you've ever seen a list of powers of 2, you know, if you're just adding repeated addition, which is basically multiplication, and you're counting by 2s, the numbers don't get big that quickly, right? You get 2, 4, 6, 8, 10, 12. grow bigger than just counting by ones, obviously, but they're not humongous numbers right off the bat. Even if you're counting by like 100, it goes 100, 200, 300, 400. Eventually you hit 1,000 and 2,000, and if you keep going, you get to 10,000 and stuff. So you do get to bigger numbers depending on how much you're counting by. But you can also kind of foresee that with the size of the number you start with. If I ask you to count by 1,000,000 every time, then yeah, you're going to start getting to numbers in the millions really quickly because I've asked you to skip 1,000,000 numbers every time. But with exponents, that might not be as evident. You know, if you're counting out powers of 2, first you get 2, then you get 4, then instead of getting 6, you know, at first we think, okay, 2, 4, 6, but no, if you keep doubling it, instead of just adding 2, if you multiply by 2, it goes 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, which is where that math game came from, that you guys might have played, 4096, and so on. So you can see that, you know, I've only multiplied by 2 a few times. I didn't do anything particularly crazy, and we're getting to huge numbers quite off the you know, right off the bat, right? Quite early on. So we did just 2 times 2 times 2 times 2 times 2. That's all we're doing, right? We're just multiplying by 2, going from here to here, times 2, going from here to here, times 2, going from here to here, times 2. That's all we're doing. We're only multiplying by 2, but we're getting to some really big numbers, right? If you did 3 plus 5, you'd get 8. If you did 3 times 5, you'd get 15. But 3 to the power 5, 3 to the exponent 5, however you prefer to say it, and you get an answer of 243, right? And suddenly your numbers are starting to get a lot bigger, even though you started with reasonably small numbers, right, to work with. So that's something to just be aware of, is that just because the question looks like it's got some small numbers doesn't mean your answer is necessarily going to work out to a number that's also decently small. You might end up with quite a large answer. But we're going to move away from the numbers for the next couple of minutes to talk about some exponent rules. So what I'm going to do is I'm going to write down the exponent rules with letters, and then I'm going to give you an example using numbers, right, so that you can see how it works. So, so the first exponent rule is, let's say you've got a base. Maybe I've named these poorly, but let's say you've got some base that we'll label as A. A can be any number, all right? So any number doesn't matter. So we've got some base raised to the exponent of some exponent b. So we've got a to the b. Those could be two numbers. Could be 2 to the power 3, or 2 to the exponent 3. Could be 7 to the exponent 7. I don't care. All right? So you've got this number, whatever it is. Could be 2, 3, 5, a half. I don't care. And this exponent is going to be some other number. I also don't care. It could be a whole number. It could be a negative number. Doesn't matter to me. And then you take this thing and you multiply it by something else, and that something else is going to have the same base. So this a over here is the same as that a over there. If this is a 2, that's a 2. If this is a 3, that's a 3. If this is, I don't know, pi, that's pi. So whatever this base is, that base is. But let's say the exponent is different. So instead of calling it b, we'll call it c. So if you've got two numbers being multiplied together, two powers being multiplied together with the same base, so that's important, the same base but a different exponent, so maybe a 2 over here and a 3 over there, for example, then your final answer as a sort of shorthand is it's going to be the same base, and then what you do is for the exponents, if they're being multiplied together, you're going to add those two exponents together. So this might be a little bit confusing with all the letters, especially if you're not used to doing math like this with a whole bunch of letters, but we're going to do an example in a sec and you'll see exactly what I mean. So basically, if you've got two numbers being multiplied together, two powers, I should say, being multiplied together with the same base but different exponents, then as long as they're being multiplied together, you can just keep that base the same and add the exponents together to get your answer. It's sort of a shorthand. It's obviously that wouldn't be your final answer. Your final answer would be the number itself, but that's sort of a shortcut for how to get there. So let me give you an example. So let's say our base is the number 3, and for the first one, let's say our exponent is 2. Alright, so let's say we've got 3 squared multiplied by, and we'll do 3 cubed, let's say. So notice that our base is the same. We've got the number 3 here, we've got the number 3 there. As long as those two bases are the same and we're multiplying these together, this rule works out. So we've got 3 here, 3 here, there. So our bases are the same, no problem. Now, that tells us that in our next line, we've got A here, A here, A here. So I know my base in the next line is still going to be 3. I don't touch the base at all. Now, since this is a multiplication problem and the bases are the same, all I need to do is add those exponents together. So my first exponent was a 2. My second exponent was a 3. So I add those together, and that'll give me, that's sort of like a shortcut for me to get to my answer. So that'll give me, if I reduce, or like if I sort of simplify that, my base is still 3. 2 plus 3 in my exponent, that's going to be 5. And we already calculated that a little while ago. That's going to give us 243, if I'm not mistaken. So that's basically the way this rule works. If the letters are confusing you, then you could just write down this example and make a note to yourself that same base, different exponent, multiplication problem, add the exponents. You know, make some sort of note to yourself like that, just so that you remember this sort of shortcut. It sort of saves you a little bit of time from having to calculate two different powers and then multiply those together. It sort of lets you do that process all in one step by, you know, making your life a little bit easier. Hopefully it is making your life a little bit easier, because hopefully you're understanding it, but if not, then I can see how it would make one's life harder. But yeah, basically, as long as the bases are the same and you're multiplying the numbers together, you can just take those exponents and add them together, and that'll perhaps save you some time in trying to figure out your answer. Alright, hopefully that's making sense. If it's not making a whole lot of sense, then I'm going to cover this in more detail in the next video, so just sit tight. We'll do a whole bunch of examples of how this stuff works in the future. But until then, I'm going to do one more, or actually 2 more exponent rules. So the first one involves multiplication, and now I'm going to get rid of this example down here. And what I'm going to do is we're going to change our rule slightly, and I think you might even be able to guess where this is going. So you might not, but don't worry about that. If you don't see it, then hopefully, through practice, then you'll memorize it, but you might already be familiar with these rules. So if you have the same base, different exponents, but instead of multiplying, we are dividing. So instead of a multiplication sign there, I put a division sign. If I do this now, a to the exponent b divided by a to the exponent c, then remember when we were multiplying, a to the b times a to the c gave us a to the b plus c. That's what we got with our multiplication rule, right? Now, if we're dividing instead of multiplying, it's quite similar. The base is still a. We don't change that. A, no problem. The b and c are still going to factor into our answer, and they're still going to be in the exponent, but instead of adding them, we subtract them. Alright, so now if you have two numbers, or two powers being multiplied together with the same base, different exponents, and you're dividing them, so if you've got these two powers, a a as the base, same base, different exponents, and it's a division problem instead of a multiplication problem, then the base will stay the same, and the exponent becomes the first exponent minus the second exponent is your new exponent. Alright, so it's a similar idea to what we had with that multiplication thing from before. It's just, it's a slightly different rule, but the idea is the same. So if we go through that with an example, let's say 4 cubed divided by 4 squared. Alright, let's say that that's what we're working with. 4 cubed divided by 4 squared. Now we've got the same base. We've got a 4 here, we've got a 4 there. So that means we should have 4 as our base in our answer. And then we've got our first exponent is a 3. So up in my exponent over there, I'm going to have a 3 to begin with. And then my second exponent is a 2. So I'm going to put a 2 over there, and we're going to subtract. Now again, remember that even though the order isn't important for addition and multiplication, it is important for subtraction and division. So it is important that you don't mix up the placement of those exponents when you're writing them down over there. So first exponent goes in the first spot, second exponent goes in the second spot. And so then if you sort of simplify that that exponent down, 3 minus 2, well, that's just 1, so that's 4 to the exponent 1, and that answer is actually just going to be 4, because that means you're taking the number 4 and you write it down one time. Well, if you only write it down one time, there's nothing for you to multiply it with, right? So you're not going to be doing 4 times anything, it's just going to be the number 4. So any number to the exponent 1 is just that number itself. Hopefully that makes sense. So basically, you take this first exponent, throw it over there, take this second exponent, throw it all the way at the end after the subtraction sign, and then you can simplify down that exponent and get your answer that way. If you're not convinced, you can try and calculate this, and you could create more examples for yourself, or you can hold out for the examples that I'll give you in the coming days. You can go ahead and calculate this. 4 cubed, you go and calculate it, and then you calculate 4 squared, and you do that division, you should get an answer of 4 to the 1, which is just 4. So these tricks do work, and they're quite useful in certain circumstances. They can save you a lot of time when you're doing your problems. So that's 2 helpful rules for if you've got 2 powers being multiplied and for 2 being divided. Now there's one more, and then a couple of little handy-dandy facts. So one more is that, let's say you've got a to the exponent b. So again, it's just 2 numbers, one number raised to another number, right? And then we're going to take that whole thing and raise it to the exponent c. So we've got, like, let's say we had like 3 squared, and you get some answer, and then you square it again, or you cube it, or something like that. Then what do? Do you have to do this thing, and then you have to do that? It just seems like a long process. First I gotta square this, and then I gotta cube it, or whatever. There's an easier way around it. There's a shortcut for this one too, which is that you keep the base the same, and then you take those 2 exponents and you multiply them together. So you could say that is BC, or B times C if you prefer, something like that. A to the exponent B times C is the same thing as A to the B to the C. So if I give you an example with numbers, that could look something like you've got 4 cubed, and then that whole thing squared. So if you've got something like that, then you would start with, alternatively, you could start with 4 cubed, which is, well, 4 times 4 is 16, times 4 is 64, and then do 64 squared. You could do that, or you could say, okay, well, my base is still 4, and then I'm going to take those 2 exponents, 3 and 2, and I'm going to multiply them together. So I'm going to have a 4 to the exponent 3 times 2, which is, of course, 3 times 2 is 6. So we've got an exponent of 6, and then you can go ahead and punch into your calculator or work it out just one time. 4 to the exponent 6 instead of trying to work out, oh, 4 cubed is this and then I have to square that and stuff like that. You can just keep your base the same, figure out that exponent, and then if you have a calculator on you, punch that into your calculator and you'll get your answer. Or if you don't have a calculator on you, then you'll be multiplying this for a little while, but eventually you'll get to the answer. So it's not going to be useful in all situations, but it's a decently helpful trick, especially when you get to a point where you're doing math that's just purely with letters and using no numbers. So basically things like this top line, it's useful to be able to sort of manipulate the equations that you're working with some of these tricks. So you would get 4 to the 6 here, and just for completeness, let's go ahead and figure that out. So we had 4 times 4, that's going to be 16, times 4 is 64, times 4 again is going to be, what, 256, times 4 again, so that's going to be 256 times 4, 6 times 4 is 24, 4 times 5 is 20, 22, 2 is 8, 10, 24, and then times 4 again, so that'll give us 4,096 would be your answer. And if you do 64 squared, which is the other way of solving this, 4 cubed is 64, and then squaring that, you should hopefully get the same thing. If you do 64 times 64, 4 times 4 is 16, 4 times 6 is 24, 25, 6 times 4 is 24, 6, 36, 38, 6, 9, nothing up there, 8 plus 2 is 10, yeah, 4,096. So you should get the same result either way. Sometimes one is easier to sort of figure out than the other, but like I said, not all of these tricks will be useful every question, but hopefully a lot of them will be useful a lot of the time. Two last things, you could describe them as rules. They're not exponent rules like these first three were. They're slightly different. So it's like if you had any number, let's say a again, and you raise it to the exponent 1, then that answer is just going to be a. So any number to the exponent 1 is equal to that number that you started with. And the last thing that you should know is that any number a raised to the exponent 0 is equal to 1, not 0. Alright, so don't get fooled. Anything to the exponent 0 does not equal 0, it equals 1. Right? So if you had like 3 to the exponent 0, it's going to be 1. But if you had 3 to the exponent 1, that's going to be 3, because it's the number that you started with. So whatever number you plug in for this a, if you raise it to the exponent 1, you'll just spit out the same number that you started with. And if you're raising something to the exponent 0, then it doesn't matter what number you plug in here for a. As soon as you raise it to the exponent 0, you're going to get an answer of 1. Alright, so those are the last couple of things that you should know. Hopefully these things are making sense. Sorry I threw so many letters in there. But in our practice examples, to give you a better feel for this stuff, it'll be just with numbers. And hopefully you'll get a better idea of how exponents work, how we can use them, why they're useful, where they're useful, and then in our future units, you might find yourself using them here and there just because they're pretty convenient. But yeah, if you have any questions, get in touch with me. Otherwise, I will see you guys not too long from now when we're doing practice problems involving exponents. Have a good one.